Looking at problem number 2, it basically asks us to explore the properties of a density function. The density function here is given like this. So we're looking at the first question. We need to find the a so as the density function is valid. Remember, the density function has several properties. One of the major properties is that it should be a non-negative function between negative infinity and infinity, and this is obviously met in this question. So we're gonna just ignore it. And the second, which is even more important, is that the integral of the density function in a whole space should be 1. And given this, where if we substitute fx with its concrete form, we could get that. But to calculate, because fx contains a delta function, which is a generalized function, we can't use the common usual way to do the integration. Instead, we introduce epsilon, which is very, very small. But we let the first interval cover the original point, that is 0, so that the first integral should be definite. And the second, it's the lower limit, it's epsilon, and the upper limit is 1. So we could calculate that by the integration. It's like that, and so the epsilon, it disappeared in the first term, but it still exists in the second term. But after taking the limit of 0, the epsilon, like this term disappeared too. So we could eventually get the formula regarding only a. So we could solve that a equals 1, which is the answer. And the second question asks us to sketch the density function. So actually, the graph is like here. The density function is it's made up of three parts. The first is a delta function, as we have stated before. Because we can draw infinity, so the graph is just a little bit out of scale, but I think we could live with that. And the second part, it's like that. It's actually a hyperbolic function. So if we draw them in the graph, in a Descartes coordination, it will be like this. And the third part, it's a constant function. It's actually 0. So the whole graph is like this. As for the third question, we need to write fx in a one-line function using the step function as a tool. To do this, we need to remember what steps function can help us. Actually, step function can be used to substitute this. The density function, it's segmented only because the second part, it's valid only when x is between 0 and 1. So we can substitute this condition by that. ux minus 1 minus ux. This is equivalent. This is actually equivalent kind of a rephrase of saying that x is between 0 and 1, and the rest of the part equals 0. So the final answer is that fx equals e inverse 2 delta x plus e inverse plus a hyperbolic function and ux minus 1 minus ux. As for the fourth question, we're going to deduct the distribution function fx is actually the indefinite integral between it's kind of an integral between of fx. Only the upper limit it varies. It's actually x. So based on the form of that, even though delta x is a generalized function, there's still we could still get that because delta x, the indefinite limit of delta x is actually the step function. So knowing that, we could easily calculate the answer. So the the distribution function is made of 4 segments too. It's like that. We introduce epsilon, but we could there is also another way to write this. We could just simply say when x equals 0, and it's like that. But we're gonna avoid the all the ambiguities. So just let epsilon be a very, very small number. And the fifth and also the last question asks us to sketch fx. So as we can see, fx is also it also consists of 3 parts. The first part is a constant function, and the second part is actually a staircase function with the jump discontinuity of e2 inverse. And the third part is also a hyperbolic function, and the fourth and also the last part is a constant function which equals 1, which means that when x is larger than 1, you see the x-axis is 1. So when x is larger than 1, the distribution function is 1. So it means the probability of x being smaller than 1, it's a certain event.